Hello guys, this is the physics past paper. Alright, let's see the questions that are waiting for us. Alright, figure 2.1 shows a cliff edge with water below it. Okay, this is the cliff, the ball. Okay, 115 meters underwater. Alright. A ball falls over the edge of the cliff. The mass of the ball is 160 grams. The height of the cliff is 150 meters. Calculate the vertical speed of the ball as it hits the water. Air resistance can be ignored. Alright. Here, the ball is falling, and since the ball is falling, its motion changes, right? And since the motion changes, that means it still with the kinetic energy, because kinetic energy is the energy that's due to change in motion. Okay, because when the ball is at the top of the cliff, it's stationary, and when it's falling, the motion has been changed. So that means the potential energy is lost here. The loss of the potential energy is equal to the gain in kinetic energy. All right, so the potential energy equals to mgh, and that is the loss change to kinetic energy, which is equal to half mv squared. Right, so the m cancels out, so I have gh equals to half v squared, and I want to find v, which is my speed here. So the v squared is equal to 2gh. Alright, so let's continue here. Therefore, the v square equals to 2 times g, which is 10, right, times the height. My height here is 115 meters, so v square is equal to 1150, and I don't want to find v square, I need to find v only, so I will square root that answer. So this cancel out is here, so v equals to square root of 1150, which is equal to 33.9. right? No, there is something missing here. Yes, I forgot to multiply the 2 out there, so okay, let's do that, which will equal to 150 times 2, which is equal to 2300, right? And the v square here is equal to the square root of this answer. So I will change my answer here in the calculator to 2300, which is equal to 47.9, which is equivalent to 48. That means the speed is 48 meters per second. Okay, it's 48 meters per second. All right, coming here to be calculate the vertical momentum of the ball as it hits the water. So I know that momentum is the mass of the ball times the speed, right, times velocity. So here is momentum is equal to um, when the mass, which is 160 grams. So I'm not going to deal with the grams here. I will change it to kilograms, which is the SI unit. So I will divide it by 1000, right? So 160 divided by 1000 is equal to divide by 1000 here, and then times what? Times the speed that I have found on part A, which is 48. So m is equal to 0.16 times 48. So let's see what's that value in the calculator. Okay, which is 0.16 times 48. It's equal to 7.68. So the momentum basically will equal to 7.68, which is equivalent to 7.7. So here is 7.7, and what's the unit of momentum? It's kilogram per meter per second. Okay, let's move on. I hope everything is clear up to here. Okay, sound waves consist of compressions and rarefaction. Explain the term compression and rarefaction. Give your explanation in terms of spacing of molecules and the pressure of sound wave in air. Alright, in compression, okay, here is the small view of how things look here. Cool. The part of the dotted diagram here where the dots are closer to each other is called the compressions, and where the dots are far away they are called rarefactions. So according to the spacing between them, I can say that compressions, the particles are closer to each other, and when the particles are closer to each other, that means there is a high pressure at that area. So, and the pressure is high. Okay, and the refraction will equal to the opposite of these two statements. Okay, the refraction here, the particles are far apart from each other, and the pressure is low. Alright, part B. A musical instrument emits a sound wave with a frequency of 4.4 kilohertz. The speed of sound in air is 340 meters per second. Calculate the wavelength of the sound. So I will recall the rule, which is speed of sound is equal to frequency times wavelength. Okay, frequency times wave, and here I need to find the wavelength. So the wavelength is equal to speed over frequency. And then let's put the values on their places. So the speed, which is 340, over the frequency, which is 4.4 kilohertz, and I'm not going to deal with the kilohertz here. I will only use the SI unit, and the SI unit of the frequency is only hertz. So I will multiply by 100, so 1000. So 4.4 times 10 to the power of 3. So let's see what's that equal to. 340 over 4.4 times 10 to the power of 3. That is equal to 0.077. Okay, and what will be the unit of the wavelength? It's meters, so it will be 0.077 meters. Alright, the frequency of the sound emitted by the instrument is changed to 5.1 kilohertz, and the amplitude of the sound is increased. With that calculation, state what happens to 1. The speed of the sound. As I know that the frequency has nothing to deal with the speed of the sound. If the frequency increases or decreases, it does not change, or it will not affect the speed. So the speed, you can say, remains the same. Alright, and to here the wavelengths of the sound. Okay, the wavelengths of the sound the wavelength of the sound will decrease. It's a matter of a proportionality equation. Since the speed is or will be the same, that means an increase in the frequency will lead to a decrease in the wavelengths. An increase in the wavelengths will lead to a decrease in the frequency to balance the equation, and all that will give me the same value of speed, which is the same for both equations I have explained here. Okay, so the wavelengths will decrease. Sound will decrease. Okay, no other questions here. Okay, see you in the next video.